companies. And what a better opportunity to partner with Superior Valley, inviting Jordan Sullivan, tech evangelist for Amazon Braket, to speak on what is the right path to becoming a tech evangelist. So without wasting any further time, I will leave the floor to Jordan and Alessandro for the talk. Thank you.
Yeah,
Thank you, Eduardo.
Yeah, so I can just go ahead and get started with my talk here. Bring up, I'm a little bit unfamiliar with Teams, so I'll take a moment here.
Yeah.
Let's see. Full screen. Doesn't like me very much.
Are you looking for how to share, right?
I am, yeah.
Okay, on top right.
Top right?
Yeah, it should be
no, so like
share.
I found the share tray, but there's no slideshow popping up, so I'm not really sure why that's it's only showing the one. Here, let me try this. Does this?
Oh yeah.
Can you see this? Okay. All right. I'll go into presentation then. Is this in presentation mode now?
Yeah.
Okay, great. Alrighty. Thanks for your patience there. So yes, hello. I am Jordan Sullivan. I work on Amazon Braket, and my job is a tech evangelist or developer advocate. And so I'm going to be talking today about my journey into quantum and some kind of like early life experiences that were around physics and quantum and kind of nerdy sci-fi stuff, and then transitioning into an actual career in this industry. So here we go. So my first memories of physics are just Star Trek, and certainly it was a lot of fictional physics in that case. Certainly we don't have warp drive yet, unfortunately, but it was always really, really inspirational to me. I was inspired by just the idea that you could use science and math and logic to understand the world and even encounter things that you've never seen before. So I always found that quite an inspiring thought. So when I was a kid, I did some kind of like early life little science experiments. I went to this desert research institute where I'm from in northern Nevada in the US, and I played around with this snap circuit toy when I was a kid, built a little hydrogen fuel cell car. So my parents were very generous in getting me very nerdy toys as a kid and taking me on like little excursions to like free science days that various research institutions were having. So I really appreciated that in that it helped me to kind of gain an early life love of science. And this is actually something that my mom recently uncovered in her basement. My like fourth grade science fair project is a very highly scientifically advanced. Rolled a skate down a ramp and measured the effects of different surfaces on the ramp on the distance that the roller skate went off of the ramp. It was my first time doing it like an actual full scale sort of, we form a hypothesis and then we test it and we take data and then we like look at what that data said about our hypothesis and write results. So it's certainly not a scientific research paper, but I would one day go on to write one. So it's perhaps my earliest attempt at doing a whole science experiment. I just thought those were kind of fun photos to share. So then, despite kind of having a real love of science when I was growing up, I think I just ended up kind of exploring other topics and other things during high school. So I did a lot of like theater, music, you know, I got very into like film, and I actually thought that I was going to study film or music or something like that in college up until a pretty much the last second, or like my last year of high school. So what happened is there's a number of things basically. So I had, as a part of a school project, that I needed to go on a field trip to an observatory. And so I went there and ended up chatting with the lead scientist at this observatory about neutrinos. They had like a little cloud chamber there, which is a type of like particle detection. And we had this really fascinating conversation about things like radiation shielding and doing that with like magnetic fields, which is what the Earth does, and the idea of potentially like using that in a spaceship to protect astronauts from cosmic rays. So I had not experienced that sort of exciting scientific conversation in quite some time, or ever. So it definitely got me thinking kind of back along the lines of getting into physics. And so I ended up in the US. The way that the end of high school works and the way that the beginning of college works is that you take all of these standardized tests, and there's kind of like a pre-standardized test that we take. This is a lot of background for this is a very brief point that I'm trying to make, but you know, bear with me. So essentially I took this like pre-standardized test, and then based on that, a lot of universities around the country will like send you brochures if they think that you might be a student that they prospectively want. So anyway, I got a brochure in the mail from you know, different colleges that were really more on the like science and technology side. And it was very surprising to me at the time. I was like, I hadn't even thought of that as a possibility. And because I had been really focusing on film and acting and singing. And so it kind of got me reigniting my passions around sci-fi. And so I started literally just Googling sci-fi technologies and seeing if they were real. Like Star Trek had essentially inspired a lot of real tech. So I mean, they had like little flip phones in their early episodes. They had like iPads, and a lot of people within tech were inspired by those things. And this happens a lot in science fiction. Like, you know, some science fiction author will like dream up an idea and like write it down, and then you know, the next generation of scientists will read it and be like, oh, that's really cool. I actually want to try and go build that. And so I was like quite intrigued by this idea. And so I was looking at different types of sci-fi technologies. And of course I was like, okay, well, could teleportation ever work? And, you know, I'm in high school, I don't know. And so, you know, it's essentially saying, well, you know, there's quantum teleportation. And I'm like, whoa, what's quantum teleportation? So I learned about quantum entanglement a little bit, as much as I could at that point. And so I started just reading a lot of books, a lot of like pop science books about physics. So I ended up reading things about quantum computing, about particle physics. And these are a few of the books that I read during that period of time. So Computing with Quantum Cats, The Universe in the Rearview Mirror, that one is about SUPER-SYMMETRY, if I'm not mistaken, or it's about antiparticles. Honestly, it's been quite a while since I've read it, but these are all really fun books to get into it, you know, when you're that age. So this is actually a picture on the right of a huge particle detector. I believe this one is in Japan, if I'm not mistaken, and it's full of liquid scintillator, which emits light when ideally the particle that you're trying to detect interacts with it. So this one's big enough that you can literally like sail a little blow up boat in it. So I just find that quite a cool image. So when I went to undergrad, I had the opportunity to do research during that period, and that was really exciting and important to me to be able to do that. And so the first research project that I worked on was another type of particle detector, which was on the study and detection of neutrinos and dark matter. So this is a picture of another of the detector that we were working on. And so this one would also be full of liquid scintillator. And so what I was doing, it's a little bit, no, I'll go into it. I'll explain what it was. So basically, when dark matter, like in this particular case, it was neutrino. So when a neutrino interacts with the liquid scintillator target that we were using, the light that it emits is too low wavelength to actually be detected by the kind of high efficiency detectors that we want to use. And so we need a way to shift its wavelength up, so make it higher frequency so that we can detect it. And so to do that, we were testing out different types of materials that have this wavelength shifting property. And so I was doing simulations and lab work around what that actually looks like and what we can expect kind of the output to look like at the output distribution. So like if you have a photon coming through, comes back out, we want to know like where is it going to come back? Is it going to go straight? Is it going to go off to the one side? Like we need to know that to accurately reconstruct where the particle was and different properties about it. So that was really my first actual research project, and it was very exciting to get to participate in it. And at the time, I felt like I knew absolutely nothing, because I probably did. But it's a nice thing about doing research as an undergrad. There's a lot of people who are very generous in these sorts of academic groups. At least that was my experience, who are willing to help you learn. So that was a very positive experience for me. So then really what is quantum computing? Because then I actually started doing research in this field in undergrad. So this is a picture on the left of a part of a superconducting quantum computer. It's often called a chandelier. It is a dilution refrigerator, which is a way of cooling things down to very low, like very close to absolute zero, like millikelvin range temperatures. And that is because superconducting quantum computers, at least superconductors that we know about, only superconduct at really, really low temperatures. So I was working on a machine very much like that one on the left and testing out a particular type of component that goes on quantum hardware, which it honestly had a kind of similar intent in some ways to the like wavelength shifting work that I did in the previous group. So what this one did was it was called a parametric amplifier. So essentially it amplifies certain signals, like electronic signals on a chip, if they fall into a particular like frequency range. And so I was characterizing what that frequency range kind of looks like what is the range over which it'll actually amplify. So that was the project that I did in experimental quantum computing. So these kind of other few images here are the one on the bottom right is fiber optics, that's photonics, and on the top right, that's a picture of what's called the topological quantum error correcting code, and that is something that I would work on later in my career. So this is actually what I did. This is the lab that I worked in. So if you look on the left here in this image, that's what's inside of both of these tubes in this picture. So it is definitely very cool to be in a lab like this, being in the basement of the astronomy building and trying to control one of these big complicated machines for the first time was very exciting for me. And I still love doing lab work when I can. It's been quite a few years since I've had the opportunity, but I find it a lot of fun. So then another research project, and the last research project actually that I did in, or the last research group that I was in undergrad was theoretical quantum chemistry. So in this particular group, I was studying small, like simple models of interacting, large scale sort of okay, so I say small systems. It's really large interacting systems with many particles, so it's called many body physics. And the particular models that I was looking at for those interactions were simple Hamiltonians. I guess I don't know the background of most people in this audience, but you know, the energy of the system, basically stripping it down to kind of a small number of like interacting pieces, interacting terms. So basically studying how much you can get out of these sort of simple models. So that was really my first foray into theoretical physics. And honestly, up until that point, I had kind of thought that I wouldn't be able to hack it. I don't know if that expression translates, but like I was not sure that I would be able to understand or contribute. And so it was very empowering, honestly, to be able to have, again, like really, really supportive people in my research group who were walking me through things and encouraging me at the time in order to make progress on these sorts of projects. So that is, again, a really, really positive experience. So then I'll just kind of like talk a little bit about some of these side projects that I did during my undergrad. I took, you know, more computer science, data science, machine learning, some of those sorts of classes. I had a really, really interesting class with actually someone I found out later was a Nobel laureate. I saw him on the wall in a picture in my physics building, and I was like, "That's Saul Perlmutter? Is that my professor? Whoa!" So that was a very wild experience. Yeah, he like measured the expansion rate of the universe, and yeah, won a Nobel Prize for it. So that was a really, really cool class, even not knowing that he was a Nobel laureate. So it was a kind of about scientific decision making, and that is definitely, it's quite impactful. It reminds me a lot of, or like it had a lot in common with this really great book called Thinking Fast and Slow, which I think I actually have a copy of it. Yes, this book, it's great. Everyone should read it. It's about like,
I know.
Yeah, heuristic. Yeah, well, it's great. You already know. Yeah. Well, for anybody in the audience who does not know, it's fantastic work in behavioral economics, and it's a lot about the way that people make kind of snap judgments and like longer term decisions. And yeah, great book. So back on track here. And some other projects that I did during undergrad where I built a Tesla coil with some friends, and let me see if I have a video. 2, 1. Yes, there we go. Yeah, so it was very fun. You know, making small light happen. And it was obviously very, very janky, not very well put together. We like ripped a transformer out of a microwave, and you know, this is made of like a pie plate and a random stack of copper rings that we found in this lab. And so yeah, it was definitely not safe, but it was fun. So then my friends and I actually started this club called Quantum Computing at Berkeley, and we were kind of intending to help connect people who are interested in quantum computing in undergrad and give them more resources to learn about quantum computing or get connected with industry and academia. So I kind of, to that end, we participated in a quantum hackathon at Braket back in 2018, and that's a picture of us at the bottom there with our prize, which was a lithographic mask for one of their chips. So essentially, when you do photolithography, if I'm remembering correctly, this particular one, you expose you expose your chip to, oh gosh, now I'm trying to remember if it's, I believe you expose your chip to light, and there are certain like compounds on the chip that react to light in specific ways to actually essentially like peel off, if I'm not mistaken. I'm probably giving a terrible explanation of this, but basically the lithographic mask is where the light doesn't shine, and so that kind of defines where the circuit is. So it's a very cool, weird prize, and I have never seen one since that has like that particular type of prize, but I would love to see that more. So yeah, then another thing that I did during undergrad in that club was on the leadership. I organized and moderated a quantum computing panel, and that's what is in this picture here in the middle. And so we had a professor and someone from IBM research and a couple of people from startups, all in quantum computing, and kind of talked about the state of the industry, how they got into the field, and what they foresaw for the the coming years, and what they thought would be the most impactful quantum algorithm. So that was really, really cool learning experience. A lot of work. People really underestimate, I'm sure, as you know, people really underestimate the amount of work that it is to organize an event. But it was very rewarding, and it was very cool to see a lot of people actually show up when we hosted it, and it was a overall very useful experience to kind of prepare me, honestly, for the sort of stuff that I do now in this particular job. So yeah. So, just a word, like if you're ever looking for a job in this field, I don't know if anybody in this audience is, but if you are, LinkedIn, very important. And even if you haven't done a lot, like all of these kind of topics on the left are worth putting on your resume on LinkedIn, because that's how people find you. So yeah. I just kind of wanted to say a word about the struggle. Like, physics, very hard, but awesome. So it's a field that'll make you feel dumb a lot of the time, in my experience. So if you're thinking about getting into quantum computing, or you're kind of like already in the field, then you don't need me to tell you this, but it's just something to keep in mind. Like, you're not the only one who feels this way. It is very challenging, but it's very rewarding. So yeah, this is kind of like how I got my first job. This is not super interesting, so I'll probably just skip ahead. But this is actually kind of like a little bit of a walkthrough of what I would do on a day-to-day basis as a quantum physicist in my first job. So actually, it was, maybe I will go back. I'll talk about this. So it was a weird experience, honestly, getting my first job, because I was in my final year of undergrad, and I had gotten I gotten a lot of rejections from various internships. I'd applied across a bunch of different companies, and just like gotten no's across the board. And I was like, oh, I'm gonna have nothing to do this summer. I'm just gonna have to keep doing research again, which, I mean, of course, so it's not like a bad thing. I do love research, but I got a message off of LinkedIn that said something like, how would you like to join a secret stealth mode quantum computing startup in Palo Alto, California? And I was like, that sounds very fake. I don't think this is a real company. So I asked around a couple of my friends and research mates, and I was like, have you ever heard of PsiQuantum? Is this a real thing? And they were like, yeah, I think I know somebody who works. I was like, all right. Apparently it's a real company. But at the time they were in like stealth mode. And what, if you're not familiar with that, basically it just means that like startups will sometimes essentially just not publicize anything that they're doing for a certain period of time, or publicize like small amounts of what they're doing for various reasons. It might be like for like keeping their technology proprietary, or they just don't want to deal with the media for whatever reason. So that's why there was not a lot of information available about it. Now they're a lot more kind of open, but at the time they were not. So Yeah, then I ended up actually then running into an employee of the company at a conference, and then having, interviews, like phone interviews on site, and then doing an internship. And then at the end of that internship, I got a full-time offer, which was really, really exciting. So then to talk a little bit about what my kind of day-to-day life was there, I really would spend a lot of time like reading academic papers and just notes that had been written by my colleagues. And there was a lot of just brand new kind of ideas and very exciting work going on at that company. And then I would write code, simulate this physics, and run the simulations and perform analysis. Also spend time coming up with new ideas to improve the future performance of quantum computers, and like speaking with my colleagues kind of across different teams about new ideas and new problems to solve. So it was very exciting. And going back to my Star Trek references, it did feel like working on the USS Enterprise. It was very, just very brilliant people and a lot of fun on a mission that I was very passionate about. So this is my job today. I work at Amazon Braket, and so I am a developer advocate, or tech evangelist, as the talk title has described. So essentially, a tech evangelist does the job of talking about a technology in a way that is ideally kind of balancing, a depth of technical detail with sort of engaging a wider audience and making sure that what they're talking about is accessible. So that is what I try to do in my talks, and I hope that this one has been not an exception to that role. So the day-to-day for this particular job is the scientific communication, so technical blogs, writing demos, creating Jupyter notebooks and writing code demos. Also giving talks. So then I also travel to conferences to give talks there, or to hang out at the booth, which is what I'm doing in this particular picture at the bottom here, and talking to customers. And I also support a lot of hackathons for Braket and attend meetups, and give talks to or really at those particular conferences, talk to quantum researchers, talk to other people who are interested in using the service, and really make it better. So like that last bit is the kind of developer advocate side of things. So advocating internally on behalf of people who use the service. So on behalf of developers, and making sure that we're building the right things for them. So that is my career. That is my journey into quantum, and I want to say thank you so much for hosting me, and I hope you had an interesting time or a fun time in this talk. So thank you very much.
Thank you, Jordan. Thank you so much. We have a couple of questions for you. We gather on a Slido. I'm going to share the screen, and then I read the question for you.
Sure.
Let me share. Okay, you should see this. Okay, I guess so.
Yeah.
So the very first question is, what is the biggest challenge in quantum computing today, according to your opinion?
Yeah, it's a good question. It's a tough question. In my opinion, the biggest challenge is very hardware dependent. So the biggest challenge for superconducting qubits is maybe different than it is for ion traps, is maybe different than it is for photonics. So really it's, building better hardware. So in superconducting qubits, and in really any type of quantum computing system where you need to use things at cryogenic temperatures, so very, very cold, scaling is a real challenge, because you can only get so big and still fit inside one of those canisters for a dilution fridge. And they make them bigger, and some of the companies are kind of taking the approach of like, all right, let's just invent bigger and bigger individual fridges. But at a certain point, that kind of has diminishing returns, and so you still need a way to translate your signal out of your dilution fridge and connect it with another one in kind of a more modular fashion. And that's a really tough engineering problem. There's a lot of tough engineering problems there, actually. So that's one at least that comes to mind. I know a little bit less about the way that ion traps, like particular challenges that they run into, because I haven't worked on those directly. For photonics, it's also going to kind of depend on the approach, because there are a couple of different ones. A challenge for photonics is, well, honestly, for any of them, scaling is a challenge, and basically connecting up modular components together in a way that you don't lose too much information connecting them, or kind of like transferring your information out of your quantum computer into like a fiber optic line and connecting it with another one. So getting those particular components to be high enough quality that you are not just ruined by loss is a really tough problem.
Okay, thank you. Next question is, how soon do you think fault-tolerant quantum computers will be available?
Yeah, that's the perennial
$1
question.
million question.
I don't know. I don't know. I don't know.
Okay. Another question. I wrote here on my phone. What is the most promising field for applying quantum computing in the near term, according to you?
Yeah, well, again, I'm probably gonna have to disappoint you. We really just don't know yet. It is really too early to tell, but that is genuinely one of the reasons that we have Braket, Amazon Braket, available for people so that they can test the current generation hardware and see where it's at and be like, okay, well, this technology might be better for this particular algorithm, or this one might be better in this situation. Like, for instance, we recently launched this Quera device, which is a neutral atom quantum computer, but it's an analog Hamiltonian simulation machine. So it is designed for particular types of problems. So simulating Hamiltonians, certainly, so simulating physics, but also running certain types of optimization problems, finding like minimum independent sets. So there are a number of applications where using a different paradigm of quantum computing could end up being more useful than using some of the more common ones. But again, it's really hard to say. Like, it's still very, very early in the field. But Braket is kind of like a nice way to keep kind of pinging that and seeing what the state of the technology is.
What are the platform? I mean, the quantum computers that you provide access by means of the cloud of AWS?
So there is IonQ Aria, which we just launched, and there is Rigetti's M3 chip, so that's a superconducting qubit machine. There is Quera, Aquila, that is the neutral atom device. There's also Oxford Quantum Circuits, which is another superconducting qubits device. And I think that's it. I could be forgetting one. Oh, we also have Borealis from Xanadu, which is a photonic boson sampling machine.
Okay, so you are providing access to different platforms implementing different kind of qubits. Okay.
That's right. Yep.
Okay, next question is, in your opinion, what is most promising in qubit implementation, superconductive ion trap neutral atoms?
Oh, I think I just answered that one.
Yeah. So yeah, right. I just read. Oh, another one. Okay. Do you think that quantum computing will be available for the public as it was for personal computing in the past, maybe mainly via cloud services?
So I doubt that quantum computers will ever be a thing that like people own just on an individual basis. I could be totally wrong about that. So, predicting the future is notoriously very difficult, especially around technology. But I don't necessarily foresee there being a real need for most people to use quantum computers, because essentially they are ultimately going to be like a very high performance computing technology. So it's in some way similar to a GPU. And I don't kind of want to like downgrade quantum computing to a computer, because it's fundamentally very different. But you can still think of it in terms of being ultimately, what we think it's going to be very good for is a pretty niche set of applications that are, things like simulating physics, like doing optimization. And just as most people don't own like a whole GPU cluster as an individual, most people probably won't own a quantum computer. Certainly universities, they might. I mean, a lot of universities already do, like own smaller scale quantum computers, government agencies probably. But yeah, probably not on the individual scale, at least that's my guess.
Okay. Okay. What kind of degree could be a best fit to study quantum computing, computer science, physics, engineering?
Well, I studied physics, and I found that to be pretty useful. It depends a little bit on what area of quantum computing you want to go into. So honestly, any of those degrees would be great for just different aspects of quantum computing, like computer science. There is a lot in computational complexity theory that relates to quantum computing. And so there's a lot of kind of like theoretical work in that area, but then there's also certainly like plenty of software engineering to be done in physics, just standard like software engineering stuff. And within quantum computing, yeah, physics obviously is really great for understanding more about the quantum aspect of quantum computing and understanding kind of what's going on a physical level. Engineering, yeah, there's plenty of engineering jobs within quantum computing. We had all sorts of engineers at my previous job where I was doing research. And really in every implementation of a quantum computer, you need people who are well-versed in things like manufacturing, in things like silicon design of chips, all sorts of things. So yeah, like all of those would be great. All those would be great choices.
Okay. Next question is, does Amazon Braket have a research section that does research on quantum computing? In that case, which kind of hardware are they researching on?
Yeah, so we definitely do. We have kind of multiple different organizations within AWS that or multiple different organizations that have different roles to play in our strategy overall in quantum. So we have the Amazon Braket team itself, which is a cloud service that offers access to different types of quantum computers. And then there is the Center for Quantum Networking, which is a quantum networks org. So they focus on essentially working on building like a quantum internet. And then there is the Center for Quantum Computing, which is down in Caltech in Pasadena, California. And that is where we are building our own quantum computer, and that is superconducting qubits.
Oh, I see. Where is based the team of AWS Braket? Is just in?
Yeah, we're a little bit distributed. A lot of the Braket applied science team lives in New York. I live here in Seattle. I think we've got a couple of people like in Colorado. Yeah, it's a little bit distributed, but I think the main contingents are in New York and Seattle.
Okay. Europe is there anyone in Europe or just in America?
Team, not on the Braket team specifically that I'm aware of, but we do have people like in other teams who also work on or work with us. So if you do live in Europe, it's there are plenty of people who work at Amazon, and even some people who work on quantum stuff who also live in Europe.
Okay, last question. What is the first kind of profitable service that Amazon Braket wants to provide? This is based on analog quantum computing?
Well, no one's really doing, well, it depends on what you mean by profitable, I guess. I would say at this stage, we don't really know necessarily what's going to be the first profitable approach, the first profitable application. That's still very much, I think, up in the air. We just need more people to kind of experiment and see, and the hardware to keep getting better.
Okay, I think that we answered all the question, and if anyone has another question, can just open the mic. Otherwise, I want to thank you, Jordan, for being here, and we will share the recording with the part of the community that wasn't able to join today. And so, thank you so much.
Yeah, thank you so much for having me. Bye.
Thank you. Bye, Jordan. Okay.